So hello again students, and welcome to the homework session on storing of biomass for energy. What we're talking about are the risks and the problems associated with storing of comminuted woody material in piles. And what I will do now is that I will demonstrate how the overall loss of material and energy may be illustrated using a very simple calculation tool. Just like we've done in earlier parts of this course, is the calculation tool not a model. It's only a way to show the consequences of guessed-in data. Now, the thing is that when you work in the bioenergy field, you will successively gain experiences and you will develop a feeling for a number of phenomena. And one of these phenomena is the degradation. And when you work with the energy planning, you will quite often have to argue about how big storage capacity is needed, where the storage shall be situated, and such things. And your arguments will of course be based on your own knowledge and experience. But when you discuss with a local politician or economist, you will have to illustrate your factual knowledge in such a simple way as to make it possible for your opponent to understand your point. And then you will have to make use of simplified models and arguments. And this calculation tool is to help you to do that. So what I've done here is to set up a simplified calculation tool for a stack of chips. So let's look at what it does, and then I will explain how. We start by setting the dry substance analysis, and I've decided to add cellulose and hemicellulose together in this case as hollow cellulose. And now I set the total amount of hollow cellulose at 60%, and I allow for a lignin content of 35%, 5% ash, and 50% moisture. Then I assume that the total amount of material stacked is 1,400 metric tons. And now you notice how the total tonnages of the components was filled in on the first line in the table. And now I enter degradation rates for hollow cellulose, and I say that this rate is 2% per month, starting from week 2 and all the way through week 20. I have decided in this case to stop the calculation at week 20. And the same way I enter a degradation rate for lignin, but I assume that that is a bit slower because lignin is a more complex component. So I set 1% per month, and I say that the rot fungi that degrade lignin establish in week 6, and then the calculation ends at week 20. Now there are two kinds of water in the material. Looking at a week, on Monday morning, the beginning of the week, there will be liquid and cold water in the material, and to escape, this water has to be evaporated, and then the vapor has to be transported out of the pile. So I say that this process is a bit slow, and I assume that only 2% of the water present in the material is vented away every week. The second type of water is that which is produced through the microorganism metabolism. That water is to some extent already formed as a vapor, and it is released in the warm part of the pile where the microorganisms are. So that water will escape to a slightly higher extent, and I assume that 10% of that water makes it out of the pile. We will now look a bit closer at how the values are computed and what can be seen from the table of results as produced by this calculation tool. Now let me explain what I did in that calculation tool, and we will begin with the in data. The dry substance analysis and the moisture content are simple enough, so there is not much to say about that. And the total amount of material is the same thing, nothing much to say. For the degradation rates, I've chosen to allow the input to be in percent per month. The reason for that is that if you find literature data, they will most often be expressed in this unit. So this is the common unit among energy people. But then I've decided to do the calculation week by week, so the percent per month number must be recalculated. And that is done by the formula you see to the right in this slide. As you see from the equation, I've set months equal to 30-day periods. To have an idea of how the total amount of energy in the pile changes, I have chosen to use the assumption that heating values are additive. You know from previous nuggets in lesson 2 that this is not the case, but you may also remember that I told you that for rough estimates and comparisons may that treatment be used. And a rough estimate and comparison is what I'm after now. So what I've done is to simply set a heating value for hollow cellulose at 15.5 megajoules per kilo and the corresponding value for lignin at 26 megajoules per kilo. And then, of course, I use the standard value, 2.443 megajoules per kilo for water. So I just add these together using the total weight as the factor. And then I set the value on the specific line in relation to the value on the uppermost line, so as to have an indication of how the energy content develops over time. Now, you will remember from lesson 1 that biomass dry and ash-free substance usually contains approximately 7% by weight of hydrogen. So 1 kilo of hollow cellulose would hold approximately 70 grams of hydrogen. And the same thing may be assumed for lignin. These numbers are very, very rough, but right now we are only doing very rough estimates. Now, you will also remember from lesson 1 in this course, if nothing else, that the oxidation of 2 grams of hydrogen produces 18 grams of water. So the weight of the water formed through hydrogen oxidation is 9 times bigger than the weight of the hydrogen consumed. 2 grams of hydrogen yield 18 grams of water, 9 times more. So then the 70 grams of hydrogen in 1 kilo of hollow cellulose will, when oxidized in the microorganism metabolism, yield 630 grams of water. And the same thing for lignin. So each and every kilo of degraded biomass might yield 630 grams of water. But some of the hydrogen is accumulated in the growing colonies of microorganisms. Let me now say that basically the same holds true for carbon in the degraded material. A fraction of that carbon will actually not be given off as carbon dioxide. Instead, it will stay and contribute to the growing colony of microorganisms. But in this simple calculation tool, I do not take into that account. It's simply not worth it, since the whole thing is so simplified anyway. But for the hydrogen and the water it is needed. And that is because the water content has such a strong impact on the total energy in the pile. So what I say in the water balance equation is that when 1 kilo of hollow cellulose or 1 kilo of lignin is decomposed, then the total amount of water in the stack increases by 0.5 kilos. So that is an implicit assumption that 0.13 kilos of water is accumulated in the growing colony of microorganisms. So then, as I said in the previous slide, looking at a specific week, there are 2 types of water. There is the amount of water by the end of the previous week, that is the number on the line above the present week. This amount is reduced by a constant percentage as given among the in data. Then there is the reduction in the amount of holocellulose and lignin. If that amounts to, say, 1,947.5 kilos, as in this case, then is it assumed that half of that amount, 973.75 kilos, is the potential amount of water that might, in the worst case, accumulate in the pile. This is equal to 0.5 kilos of water per kilo of holocellulose and lignin, as we said earlier. But then again, is this amount reduced by a percentage that is given among the in data? So in this specific case is 10% of the new water, 97 kilos, given off as vapor. And then 2% of the water that was present in the pile at the end of the previous week, 2% of 648.3 tons, almost 13 tons, also escape. So the total water content in the pile changes. This type of very simple reasoning may be used to convince, for example, politicians that the handling of the material must be optimized so as to avoid unnecessary costs, that is, energy losses, in the supply system. So I would suggest you make yourself a similar tool. In the long run, as you gain experience, you will get yourself a set of reference values when it comes to how fast different components and types of biomass may degrade. So you will learn successively to make a proper use of a simple tool like this. But so far, you just have to trust me. This type of simplified calculations is very useful when you look at existing systems and also when you are in the planning stage. So now I want you to do two things. First, make yourself a simple tool like the one I just showed you. Second, download the paper by Ba, Prince and Prodon. You will notice that the paper assumes that the final destination for the biomass is a biorefinery, but that will have no effect whatsoever on the supply system. Reading the paper, you will notice how the authors specifically point out that the expenses associated with storage are often underestimated. If you look at figure 4 in the paper, you will see an example. You have to remember that what is called costs in the paper is what I call expenses. Losses, real costs in terms of energy and thermodynamic inefficiency, are really not treated in the paper. So use the methods taught in this lesson, how to estimate the costs for the different steps in the supply system, and then set up a diagram for the costs associated with individual steps. Not the expenses, the costs. Compare that estimate to figure 4. Apply a critical mind now to the methods. What in data do you have to provide? How accurate are the in data? How complicated are the calculations? What is predicted? Do you think that the accuracy of the predicted expenses is very much higher than the accuracy of the cost predictions you get by doing rough estimates the way I've taught you in this lesson? I'm not arguing that linear programming should not be used for predictions concerning expenses. The only thing I'm saying is that sometimes it's a good idea to accept that the in data are so insecure that you should not go into excessive efforts in the treatment of the data. The results will not be more accurate than the in data anyway.